Welcome everybody to Probability and Analysis webinar. It is our great pleasure to have today Noam Lifshitz from the Hebrew University in Jerusalem, who will tell us about product mixing in compact Lie groups. Noam, feel free to start.
Thanks for the invitation. So the theory of the Boolean cube and the noise operator has found remarkable applications in various fields. For instance, there's lots of applications to theoretical computer science, to phase transitions, to percolation, to social choice, and extremal combinatorics. And today, for me, I guess it's tonight, we'll talk about a new direction, basically, that relates this theory of the Boolean cube and puts this in a more algebraic perspective. So basically, relates it to group theory and to probabilistic problems in group theory, and also to representation theory. Okay. 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 So we're going to discuss a variant of the following problem. We're going to have a group G, and in our talk we will be mainly focused on compact Lie groups, such as the special unitary group. Okay, maybe before the problem, let's give a definition. A subset A of G is said to be product free if for all A, B in A, B is not in A. So that's the opposite of being a subgroup. So for each two elements in the set, the product is not in the set. And the following problem was posed by Baba and Josh in 1985. They asked how large can a product-free subset of a given group be? Of a finite group GEB. And then and they had this conjecture. Okay, so they had some conjecture. But 2 years earlier, 2 years after, they conjectured something, and they also like posed AN as as an example, this problem makes more sense somehow for simple groups, and they therefore pose the AN as a first example in that paper. And in 1987, yeah, so basically they conjectured that there always exists a product-free set of density omega of 1. Okay, so they conjecture there exists a set whose size is the size of G over 100, something like that. And in 1987, actually, Kedlaya conjectured the opposite. So he gave some construction of a product-free set. And conjectured that its contraction is optimal. And the construction basically, you have a group and suppose that it acts on some set X. And suppose that also that you have a subset I. You have I that's a subset of X, and you also have an element X in X. So given this, you can construct a product-free set. You can set A to be the set of elements in G, such that G of X is in I, and G of I is contained in the complement of I. And basically, Kedlaya's conjecture was the case where G is AN, which acts on the set 1 up to N. And then you can take X to be 1 if you want. And I to be some set 2 up to M for an appropriate M. And okay, so basically in 1985, there was one conjecture, and then in 1987, there was a competing conjecture. And Gowers, in a very influential paper from 2006, where he coined the term quasi-random groups. He showed that basically he refuted the Babay-Shosh conjecture. And he showed that every product-free subset of AN has density at most n to the minus 1/3. So size at most n minus 1 to the minus 1/3 times n factor. This was then improved by Eberhard. to n to the minus 1/2, like O of n to the minus 1/2 log n to 7/2, if I remember correctly. And then together with Kivash and Peter Kivash and Dorminzer, so we determined exactly the largest product-free set in AN. For n sufficiently large, this confirmed Kedlaya's conjecture. Okay, so that's an aside about AN. Are there any questions before I move to compact Lie groups?
And what density do you get in this case?
Yes, so the density is n to the minus 1/2. So basically you get so basically you look at this construction. So it's the set of elements that set of permutations that send 1 to the set 2 up to m. So you take m to be of size roughly root n. So this happens with probability 1 over root n. And then the probability that you send I to its complement, this is a constant. This is a birthday paradox. So so basically if you optimize over the parameters, you get roughly 1 over root n. And basically we use the ideas from the Boolean cube. Basically somehow this example resembles dictators, but our main focus would be the case of compact Lie groups.
Can I ask one more question here? When you say you confirmed Kedlaya's conjecture, meaning that his construction essentially is the only one also that gives this largest size, or you can find other? Okay.
Yeah, we showed also that equality is attained only for the sets of the above form. Yeah.
Okay, thank you.
And also like a stability result. Okay. Cool. Okay. So, okay, and basically Gowers, when he refuted the Babai-Shosh conjecture, he also posed the following problem, corresponding problem for compact Lie groups. So now it's basically the same thing. Now G is be a compact group. So if G is a compact group, there exists okay. Yeah, so recall there exists a unique harm measure, probability harm measure. That which means that, yeah, so it's both left invariant and right invariant. So mu of GA is equal to mu of A and equal to mu of AH maybe for all measurable A and G and G. Okay. So the problem is, given what is the largest possible mu of A, when A is product free. Yeah, so basically the same problem makes sense for compact groups once you replace the density of A by the measure of A with respect to the probability Haar measure. Okay. And in particular, yes, we asked this problem for G, which is the special unitary group of all elements such that that are unitary and have determinant 1. Okay, and asked what's the largest possible product-free set there. And there you can find an example. So it specifically conjectured that every product-free subset of SUN is measured at most e to the minus Cn. And what he proved was n to the minus 1/3. So he left basically an exponential gap between what his methods were able to obtain and the construction. And the construction, it corresponds to also to some group action. SUN acts on the complex sphere. And then you can take the set of elements, send the North Pole close to the South Pole. So let's say A of E1, set of matrices such that A of E1 is close to minus E1. And unitary matrices preserve distances. So this would mean that if this is our set A, then and if A and B are in A, then this would imply that BA of E1 must be close to E1 and therefore not close to minus E1. And so you choose the parameters to optimize the definition of closeness. But anyways, this is since the sphere is of dimension 2 and minus 1, the size of this product-free set is going to be e to the theta of n. So if we send the North Pole into a small ball around the South Pole, then when you apply another matrix, you're going to go from here back to near here, because intermatrices preserve distances, and then this implies that the set is product free, and it has measure e to the theta of n. Remarkably, this problem was posed completely independently by physicists that they were interested in basically quantum communication complexity. Yeah, so basically, suppose that you have yeah, so there were physicists that tried to construct efficient quantum communication protocols, which means that so this means that people, you communicate by sending qubits to one another. Okay, and but when you try to show that you're yeah, so basically if you basically in most of these yes, I'm talking about things that I'm not, I don't want to 100% understand, but I'll say it anyways. So basically when you try to communicate using qubits, the problem with qubits is with in the physical world is that they have lots of noise, and when you and sometimes you can show that whatever you try to do using qubits, you can actually do using classical computers. And then you would like to design experiments that show that some things are easy to do using using actual qubits, but are hard to do classically, or trying to obtain separations between these. And then you can make experiments that show that you actually constructed qubits, and without too much noise that make them as good as classical ones. And yeah, and then they designed some experiment, and then they wanted to show that, yeah, so they designed some problem. Basically, you have, I'll talk about it. So you have Alice, Bob, and Charlie, and they want to determine whether ABC is equal to the identity. And, yeah, so Alice gets matrix A, Bob gets a matrix B, and Charlie gets a matrix C, and they want to determine whether ABC is I or ABC is minus I. So they're promised that one of those is true, and they want to determine which is which. And basically, you can show that it's easy to do using quantum communication, but hard to do. But then they wanted to show that it's hard to do classically, and then they had this conjecture that's strengthening of Gauer's conjecture, at least in the qualitative sense, but not in the quantitative sense. Okay, so that's, I mean, it's not too important, all of this stuff, but anyways, it's sort of nice to see that people go to the same problem from an entirely different angle. And yeah, so that's the product mixing conjecture. which was posed by physicists. So they conjecture the following. Suppose that A, B, and C are subsets of SUN of measure at least e to the minus c and to the 1/3, where c is a sufficiently small absolute constant. Then when choosing A randomly out of A and B randomly out of B, the probability that A, B is in C is in the interval mu of C times 0.99 to mu of C times 1.1. Okay, so basically it implies something much stronger than mixing time 2. So basically it tells you that if you take A out of A and B out of B, their product is mixed. But it's so mixed that even if you ask what's the probability that is in a tiny set of measure e to the minus c and to the 1/3, the probability is very close to its measure. And here e to the minus c and to the 1/3 is sharp. And the relation to Gauer's problem is that you can take, so for Gauer's, you can take A to be equal to B and equal to C. And then a product-free set, the probability that A, B is in A is 0. So if that conjecture is true, then it would imply it would give a bound of e to the minus cn to the 1/3 for Gauer's problem. Here is the Gauer's problem. Every product-free subset has measured at most e to the minus cn. Okay, so are there any questions so far? Okay, by the way, when I say that A is informally random out of M, formally it means that A is chosen according to the Haar measure, and we condition that A is on A, is in A. Okay, cool. So let's state our theorem. So basically we proved several results, but I'll just say state 2. So one of those results is that the product mixing conjecture is true. So again, this implies that for every three sets of measure at least e to the minus cn to the 1/3, the probability when you choose A randomly out of A and B randomly out of B, the probability that AB is in C is roughly the measure of C. And we also proved a mixing time result. And that's also sharp and easier to explain why it's sharp. So yeah, so basically suppose that A and B are subsets, measurable subsets of SUN of measure at least e to the minus cn to the 1/2. Then when choosing A uniformly out of A and B uniformly out of B, AB, the distribution of AB is close to Har. Yeah, so let's say the distance from the Har measure is at most 0.1. Okay, so basically there are various works about random walks in calligraphs. Where you take a random element from A and you multiply by it. And basically this theorem tells you that for every calligraph over the special unitary group where A is measure at least e to the minus c root n as mixing time 2. So which is somewhat surprising, I guess. And the sharpness example is to take the product. Okay, so here it's yeah, so for here it's easy to show sharpness. You can take all the matrices in SUN such that the real part of A11 is at least n to the minus 1/4. Now the real part of A11 is distributed it's not exactly distributed, but it's close to being like a normal random variable with expectation 0 and the variance 1/n, and basically A corresponds to n to 1/4 deviation from the mean. So the measure is so we expect the measure to be e to the minus root n roughly, and indeed it is. But when you but if you choose A and B out of A, then the real part of AB11 gets 1 over n boost, which is a single deviation from the mean, so it's not mixed. Okay. You can construct a similar example to show that sharpness for the product mixing conjecture. So basically, Morley result says that this example is the slowest mixing somehow, at least up to a constant in the exponent. But one open problem, but Gauss problem is still open. And it would require new techniques because our results, basically, our methods don't distinguish between mixing, the product mixing conjecture and product-free sets. And to solve Gauss problem, we probably need to find new ideas. Okay, but let me tell you about the proof. So how much time do I have, by the way?
I think 12 minutes, something like this.
12 minutes, okay.
Yes.
Okay, so I'll tell you some things about the proof. And basically, the ideas are related to ideas from the Boolean cube. Okay, so basically, Gauss result is really Gauss proof was based on ideas of Sarnak and Shui. Okay. So Gauss coined the following definition. So it says that group G is a D quasi-random. If for every representation rho from G to every representation of dimension less than D is actually the homomorphism that's always equal to the identity. It means that every representation of dimension at most D minus 1, the representation is basically, the group acts trivially on all the elements in the space that you acted upon. Yeah, so this is for every homomorphism. And basically, this notion is about being very non-abelian, because abelian groups have representation of dimension 1, and here a group is quasi-random if it has no small dimensional representations. And Sarnak, Shui, Gauss lemma explains why this notion, which is very algebraic, why it's called quasi-randomness. It's the following. Sarnak and Shui put it in a slightly different context of earlier, of a group acting on a set. It's related to the spectral theory of automorphic forms. and Gowers used it in the context of product-free sets. And what they prove is the following. So suppose that F and G are in L2 of some compact group. D quasi-random compact group. Then F convolution G minus the expectation of F times the expectation of G. The L2 norm of that is at most the 2 norm of F times the 2 norm of G divided by root D. Okay, so I'll just say that what the convolution is. So F convolution of G at X is the expectation of F of Y, G Y inverse X. So basically, this is this lemma is a remarkable property of quasi-random groups. Basically, you have two random variables, Y and Y inverse X, and the product is always equal to X. But even though we know something about the product, these random variables behave as though they were independent. Basically, you can approximate the convolution of F and G with the product of the expectations in L2. So basically, you get that Y and Y inverse X behave like independent random variables. And this was the key ingredient behind Gowers' proof. And basically, it turns out that product mixing, so I don't have time to explain fully why it's true, but product mixing turns out that if you let F be the indicator of A, and G be the indicator of some B, and H the indicator of C, you can sort of write it more analytically. The product mixing for the set corresponds to the convolution of F and G in inner product with H being close to the product of the expectations. So if you can approximate F convolution G with the expectation of F times the expectation of G, then it means that the inner product you can approximate by the product of the expectations. This is easy. And this was basically Gowers' idea in refuting the Babai-Shosh conjecture. But the only problem that in SUN is only n quasi-random. Okay, so Gowers' result, basically you get only n to the minus 1 over third. When you want something exponentially better, and in order to do that, we use the ideas from the Boolean cube. So one theorem due to KKL, or maybe BKS, I'm not sure. Basically, KKL proves something slightly different using 4 norms, but then you can use Q norms to obtain the following. Okay, so suppose that F is a function from the Boolean cube Okay, actually, it's more convenient to write it like that. So suppose it has expectation alpha, which is at most 1/2, and a Fourier expansion then you can say that most of the Fourier mass of F is concentrated on the high degrees. So the sum of the Fourier coefficients squared over all S of size D, this is like alpha squared. So the trivial bound would be that it's at most the 2 norm of F, which is alpha, but it's at most alpha squared up to logarithmic factors. Okay, and here you need D to be at most log 1 over alpha. Okay. And C is an absolute constant. Okay. And the way to think about it is that the Fourier mass of Boolean functions of small expectations is concentrated on the high degrees. So it's proved via Bonami lemma or via hypercontractivity. And basically our idea was to generalize it to the special unitary groups. So basically, what you can do in the unitary group is you can define the space V at most D to be polynomials of degree at most D in the entries and their conjugates or maybe you can think of it as I don't know, a unitary matrix. You can think of it as having 2n squared variables. You have the real part and the imaginary part, and then you can take polynomials of degree at most D in those parts, and then you can define V equal to B D to be V at most D intersection with V at most D minus 1 orthogonal part. And we proved a level D inequality. So suppose we prove that suppose that F is a function from SUN to 0, 1. So the indicator of some subset, and the expectation of F is some alpha smaller than 1/2, and D is at most log 1 over alpha. Then we get, but also smaller than root n for some technical reason. then you have the same inequality. So the same inequality means that when you project F to this space V equal to D, the two norms squared. Yeah, so when you do the same construction over the Boolean cube, you get exactly the same Fourier expansion as the sum of the Fourier coefficients at level D. You get exactly the same thing, that this is at most alpha squared times C to the D log to the D of 1 over alpha divided by D to the D. And basically this is one thing, and another theorem is that the minimal dimension of a subrepresentation of V equal to D has dimension at least Cn plus D over D to the power D for some C greater than 0. So basically, if you look back at the Sarnak-Shue lemma, you see that basically the dimension of the representation works in your favor, and the higher the dimension of the representation is, the better the approximation you get here. And what we proved is that basically the representation grow. Okay, so basically, I guess themes are that the dimensions grow rapidly with D, but most of the levels, most of the Fourier mass is concentrated on the high Ds. And you can use these two facts together to prove the product mixing conjecture. Okay, so I think I'm out of time, so I'll stop.
Thank you very much for a wonderful talk, Noam. Are there any questions? Maybe I'll ask a couple of questions. This D-level inequality on the Boolean cube, do you know if it is sharp and what are the optimizers for
so the level D in the Boolean cube, it's basically sharp for basically.
What are the optimizers?
Or just to take, yes. So basically, it's sharp also in the Gaussian setting, and you can simulate the Gaussian setting inside the Boolean cube. So
yes.
Yeah, so the level 1 inequality, okay, would be sharp for some threshold function, I guess. Yeah. Yes. So basically,
half space in Gauss space.
Yeah.
Half space. Okay.
This is for the level 1 inequality. For the level D inequality, you can take, I guess, x1 plus xn over D divided by root n over D times. Yeah, but actually, I think some half space is enough. But yeah, probably half space is enough. I don't think we need this.
Maybe again half space. Right?
Yeah, just half space would be sharp for the level inequality. So.
And how do you get this in the case of groups? The similar inequality. What kind of hypercontractivity do you have? You have linear product. What else? But you want some moment inequality or something like this, right?
Yes. So
Can you say
okay.
one sentence if it is not too long? I don't know if it is, then we'll
Yeah.
look at into the
So we
paper.
have two proofs that basically that one of them is sharper, and the other proof basically gives you something slightly weaker, but it also works when d is larger than root n. So one idea is to basically take the heat kernel of the Laplacian so you take the heat kernel of the Laplacian, there is a Bakri-Emery criterion tells you that a lower bound on the Ricci curvature of SUN implies hypercontractivity of the seed kernel. And then, and representation theory tells you something about the eigenvalues of the Laplacian. So that's one proof that doesn't give you the optimal product mixing inequality. But somehow, when you have hypercontractivity for an operator, you immediately get some moment bounds for the eigenfunctions.
Yes.
And the moment bounds, you need to calculate the eigenvalues, and there are some formulas for the eigenvalues using representation theory. So this is like one proof, and the other proof is more probabilistic. And the idea is to you couple SUN with a Gaussian space. So with the Gaussian space, by applying Gram-Schmidt on yes, you have like a random matrix that's not necessarily unitary, and then you can apply Gram-Schmidt to get a unitary matrix. And okay, so using this coupling, you have an operator. So an operator, I guess, T from L2 of SUN. Okay, so let's see if yeah. Okay, so I have an operator T from L2 of SUN to L2 of Gaussian space by taking by setting T f of A to be f of Gram-Schmidt of A. So you have
A is from SUN or just some arbitrary matrix?
So yeah, so T is from L2 of SUN to L2 of R to N times N with gamma. So basically, TF takes as input some arbitrary matrix, and then it applies Gram-Schmidt. And then what you can do is basically look at T composed with the noise operator, composed with the adjoint operator, T star. And that's almost what you do. So basically, the crucial property of this coupling is that it's measure preserving. So you can show that when you apply Gram-Schmidt, then it's going to be invariant under multiplication from the left. And it turns out that this automatically implies that this operator it implies that T and T star are contraction with respect to every LP norm. So it automatically implies that this operator is hypercontractive, where T rho is here is the Ornstein-Uhlenbeck operator. So this operator is automatically hypercontractive. And then usually I guess it's called U or something, or UE to the minus T. If you want, you can call it like that, and then you modify it a little bit. So basically there is an arbitrary choice of basis, so you can sort of symmetrize this operator by choosing a random basis first and then applying this operator. And it turns out that when you do that, you can compute the eigenvalues. Yeah, so that's basically the main challenge. Yeah, so the challenge is to compute the eigenvalues of this operator, because this operator is hypercontractive for free, but it doesn't help you to have a hypercontractive operator unless you can say something about its eigenvalues, because you can always take the expectation to be hypercontractive, and the way you compute eigenvalues is you use representation theory, and basically the idea is somehow that so one idea is somehow to show that every eigenspace inside V equal to D for D smaller than root n contains a nice function. So this you can do using representation theory. So this nice function we call the comfortable disjuntas. Yeah, so basically, if you look at the usual noise operator at the Boolean cube, you can see that the eigenspaces that correspond to degree D, each of them contains the characters, which are disjuntas. They depend only on D variables. Turns out that in SUN there is a similar phenomena that basically in V equal to D, you always have a function that depends on the upper D times D minor. And not only does it depend on the upper D times D minor, it's a very nice function of the upper D times D minor. It's multilinear. It's a function of the form sum over sigma, A sigma times the product over I from 1 up to D of xi sigma I. So it has a very, and sum over sigma in SD. So it's a function that depends only on the D times D minor, and it's also multilinear. So they're very nice functions. And then you can compute eigenvalues by applying the eigenvalues of T by applying it. So not of T, but for the composed operator, the final operator, I don't know, let's call it T tilde, by applying it to this function, to a comfortable disjunta. And then the intuition is that the variables in the upper D times D minor behave like independent Gaussians.
Yes.
And the random walk that corresponds basically to so the random walk, basically you go from the unitary space to Gaussian space, then apply noise in the Gaussian space, and then you go back. This random walk corresponds to independent noise, turns out. Okay, it's not exactly independence, but to almost independent noise. That's at least the intuition. The proof itself, there were like lots of tricks to make it actually work, but that was the intuition, that you have this function that depends on the upper D times D minor. This random walk behaves like independent noise, and therefore the eigenvalues should be the same eigenvalues as the eigenvalues of the actual noise operator. And yeah, and it works. Yeah.
No, maybe I will ask you one more question. I missed this. How do you define polynomials on SUN of degree D? These are just usual polynomials, and you plug unitary matrices?
Yeah, so you have your matrix, and let's say if you A11, yeah, real of A11, okay, I guess I defined, yeah, real of A11 is of degree 1. And A11 squared is of degree 2.
Ah.
Yeah, so we have like, you have 2 n squared real variables, and you take polynomials of degree D in these real variables.
I see, okay.
And yeah, the point, the point is that in the Boolean cube, basically, you can define V at most D. Basically, you can do the same. You can take polynomials of degree D, of degree D in the coordinates that's in the Boolean cube. So these are the polynomials of degree at most in the coordinates, and then you can do the same thing and take V equal to D to be V at most D intersection with V at most D minus 1 orthogonal part, and then the sum over S equal to D of F at S squared. This is the projection of F to V equal to D.
Yes.
2 squared. So basically the same notion generalizes. And it turns out that this decomposition, which is elementary, we really like in the Boolean cube, turns out that this has representation theoretic interpretation. This is the decomposition of this space. Into irreps with respect to the group Sn semi-direct product with Z-mod 2 to the n. This is called the hyperoctahedral group, and Z-mod 2 to the n acts by reflection, and Sn acts by permuting the coordinates. And turns out that this decomposition, this is basically the group of symmetries of the hypercube, and the noise operator commutes with it. Basically, it preserves the symmetries of the hypercube, and it explains sort of why this is the spectral decomposition of the noise operator. And basically this is so this also has like representation theoretic interpretation, and you can basically, and you get the same theme that high D corresponds to high dimension, but the Fourier mass is on the high D.
And one last thing, Noam, when you say that this level of inequality is sharp, you mean up to constant C, right? There is this constant C. Okay.
Yeah, I don't remember if we know the right C or not. This I don't remember.
Okay.
And it turns out that this thing is like, yes, so I talked about SUN, but you can do it actually for all compact Lie groups. And it turns out there are analogs for the symmetric groups and for classical groups like SLN FP and its cousins. So it's basically the setting of the Boolean cube is a special case of something much more general about groups of high rank with this n tending to infinity. For all of them, you have a similar phenomena. That
Do you have it written? Do you have it written somewhere in your papers where we can read it?
Yeah, for compactly groups, it's out on the archive, and we're working on writing everything down for. I mean, for SNNFP, we have a draft that we should just put on the archive at some point, maybe soon.
Yeah.
And we're working on writing stuff for the other classical groups. We have this group ONN of FP and UNN of FP. And
that's very interesting. That's very nice.
And it turns out that the representation theoretic part of this, to say that there is this parameter D that corresponds to high dimension, this is a recent theory. It's not like something too old. It's like something from like there are like these papers by Guanlik, Larsen, and Tiepp, and then by Larsen and Tiepp that are like.
You said it's a recent theory, right? Not very old.
Yeah, it's a recent thing. It's like something from 2019. This idea that there is this level parameter D, that the dimension go with D, and they didn't have level D inequalities, but what they had instead is it's actually quite amazing that they had this parallel theory about basically they didn't prove level D inequalities, but they proved character. That's what, like in a recent work by Guanlik, Larsen, and Tiepp, they proved basically they had one representation theoretic ingredient of lower bounding the dimension of the representations in terms of D, and then they proved something about moment bounds for the characters.
Okay, thank you very much. Any other questions in the remaining in the audience?
I had one more question. You said that this also has a consequence on the mixing time on K-Lake graphs. But
yes.
to get to 0.1 of the Haar measure, right? If you want to get to even closer,
so so the distance to Haar measure is going to be if the measure is like e to the minus c root n, you're going to be like I don't know, e to the minus m, let's say, then you're going to be m squared over n close to Haar, something like that.
I see. And this is sharp, or we don't know? It's just a consequence.
This I think is sharp. Probably the same example would show sharpness. Yeah.
Okay, thank you.
Okay, I think we asked quite lots of questions. Thanks, Noam, again for the wonderful talk. Okay, I will stop recording.